Welcome back. In this class, I would like to give you a brief idea about what an NMR spectrometer is. There are several components, several parts in NMR spectrometer. Each will do its own job. Of course, this is not absolutely essential for this course because this course is devoted mainly for 1 and 2 dimensional NMR applications for the chemists, principles, concepts, and applications. However, needless to say, you should know something about the spectrometer and also something about data processing, data acquisition, etc. So I thought I'll give you a bird's eye view or a brief discussion about what an NMR spectrometer is, various parts of it, what it does, and some tricks involved. So this is an overview of an NMR spectrometer. Remember, an NMR machine is basically a FM radio. It is a radio frequency, it comes under radio frequency region. It is nothing but a FM radio. What important thing is, remember, the broadcasting station is not Bangalore, Dharwad, Mysore, etc. But broadcasting stations are different nuclear spins. And receivers are like individual houses. We are individual spectrometers are the receivers. So radio frequency signal emitted by the nuclear spins after doing certain trick in the experiment by sending radio frequency signal, exciting the spins and collecting the signal. We do the Fourier transformation and collect the peaks. This is nothing but a FM radio. Okay. So the signals are now emitted, broadcasting station, you can assume like different nuclear spins. This is a schematic illustration of a modern NMR spectrometer. It consists of a magnet, which is superconducting magnet. I will tell you as we go ahead further. And we have a probe which is put from the bottom, and you have to insert the sample from the top. Nowadays we have a robot to do that job. We have a preamplifier, the signal detected, the EMF induced, we collect as small microvolts or very small amount of voltage is collected. That is very small. It has to be amplified by a preamplifier. Then it is taken to the spectrometer, do all sorts of processing. And of course, we have a transmitter to transmit the right radio frequency signal or the pulse. And in the same, we also collect the signal, do the digitization, and give to the spectrometer interface, which we call as a console. Here, all operations will be done depending upon what is the command the operator gives. Various functions are carried out, and this is a host computer where your time domain data, frequency domain data, pulse programming, various things can be monitored here. Of course, major important component of the spectrometer is we have a gradient control also. Most important is a 2H lock. We have a deuterium lock to prevent the field from drifting. We have a lock transmitter, lock receiver, and important, we have field shim regulation. We have shim currents here, shim coils, where we pass the current and generate a counteracting magnetic field to nullify the field inhomogeneity, to make the magnetic field homogeneous. And of course, all the experiment, in spite of it being a superconducting magnet, nowadays magnets are superconducting, and room experiments are carried out at room temperature. And this sample temperature, if you want to study the dynamics, can also be regulated, can also be monitored. So this is basically a schematic of a block diagram of an NMR spectrometer. And just to give you brief description about the components, it requires an intense, homogeneous, and stable magnetic field. Remember, 3 words: intense, that is very strong magnetic field, very high magnetic field, homogeneous, over a sample volume of about 1 centimeter, 3-4 centimeters, in which you have put the sample at the receiver coil is there. Over that entire receiver coil area where we are going to collect the signal, the magnetic field has to be perfectly homogeneous. The homogeneity should be 1 part in 10 to the power of 10. So that in a spectrometer of higher frequency, like 600 megahertz, 1000 megahertz, you must be able to differentiate 2 peaks separated by 0.1 hertz. That much is the resolution you require. So magnetic field has to be perfectly homogeneous. And it has to be stable. Field should not drift. Magnetic field invariably keeps changing, drifting in this. So the position will change. When the magnetic field drifts, what will happen? You will have multiple resonances. Peak gets distorted. It has to be avoided. So you need a intense, homogeneous, and a stable magnetic field. You need a probe. Probe has a coil, RF coil. It does the job of both excitation and detection of the signal. There is a coil in the probe, which I showed you in the previous diagram, which is inserted from the bottom of the magnet. The radio frequency pulses when you send, you will excite the nuclear spins. That's the same coil which not only acts as a transmitter, also acts as a receiver. It receives the signal, detects the signal. So of course, high power transmitter is required to generate the frequency and send a short RF burst of pulses. We need to have a sensitive receiver to amplify the NMR signals. I showed you the signals what we are going to generate. EMF is of the order of very small microvolts, and we need to amplify it. We have a pre-amplifier to amplify the signal. Then we have another amplifier. So finally, we should be in a position to detect the signal and digitize it. So I have a digitizer because the signal is collected in the digitized manner. And then afterwards, we need to have an analog to digital converter for that, a pulse programmer to do the job of all those things. We need to precisely time the delay of the pulses, angle of the pulses, phase of the pulses, everything we need to precisely monitor, manage it up to nanoseconds, up to microseconds. So require a very good pulse programmer. And of course, for all this operation to control and manipulate and deal with it, you need a sophisticated computer which does the job of operation and processing of the data. So this is how the pulse FTNMR spectrometer console works. Console is for a small block diagram of 250 megahertz. You have it is a super heterogeneous circuit is there. As I said, there is a probe, and then of course the synthesizer generates the frequency here, sent to the mixer, transmitter, and then we will send this signal to the probe, and we receive the signal, give it to the preamplifier, and then again mix it and all these things. We do few things and detect the signal. Signal is sent back to the computer, and we can also monitor what we can do through the pulse programmer using the computer, and we can also monitor the transmitter frequency, everything, and all this preamplifier, everything is controlled by these things. And so this is basically a block diagram of 250 megahertz. How it was, everything is a detailed discussion of each and every component. Let us not worry too much. I just wanted to give you the brief overview, bird's eye view of NMR console. Let us go to the types of magnets. It is very important. Broadly, magnets can be classified into two types. One is air core magnet, other is iron core. Two types of magnets are there. Of course, in the iron core magnets, all of you would have understood in your early college days, you have a permanent magnet and you have an electromagnet. So long as the positive current, you have a magnetic field. That's fine. In the air core magnets, again they can be divided into two types. One, you can have a magnet at room temperature, and you have a magnet at superconducting temperature. It is a superconducting magnet. This superconducting magnet generally in the present day spectrometers is done at cryogen temperature. That is at the liquid helium temperature, which is at 4.2 K. Now, of course, we can go further. So we have very high field magnets working at 2K. So it's okay. But you can also have a high Tc superconductor. But presently, the most popular and routinely employed, which is powerful, available commercially, is superconducting magnet, which works at cryogen temperature, liquid helium temperature. So what are the maximum magnetic field that you can achieve in all these things? Of course, if you have an iron core magnet, maximum magnetic field that you can achieve is 2.5 Tesla. Remember, the unit of magnetic field, I discussed earlier also, 1 Tesla is 10,000 Gauss. So whether it's a permanent magnet or electromagnet, maximum achievable is 2.5 Tesla. Beyond that is not possible. Okay. Whereas superconducting magnets has an advantage. You can get the magnetic field beyond 21 Tesla, so that you can get even a 900 megahertz spectrometer if is possible. Of course, nowadays even more, 1 gigahertz, 1.1, 1.2 gigahertz spectrometer will come to the market soon. it will be commercially available. So we are spectrometer frequency is going up and up. As a consequence, the magnetic field strength also is very high. And to generate such a magnetic field is enormous amount of research. We cannot just generate a magnetic field so easily, just because we know the superconducting nature of a certain material and then make it superconducting, positive current, generate the magnetic field. It is not all the time true. There is a lot of work involved in that, lot of technology, lot of research has gone, and now people are able to get very stable, strong and homogeneous magnetic field for 900 megahertz, 1 gigahertz, and 1.1 and 1.2 are also available. 1.2 will come to the market soon. So present day spectrometers always work on persistent current mode, that is called superconducting magnet. What is a persistent current mode? See, what is persistent current mode is if you pass the current, take a material, make it superconducting, pass the current, generate the magnetic field, then seal both the ends of the wire. That's all. Join both the ends of the wire. Now you don't need external current at all. So long as you maintain the liquid helium temperature, the coil is immersed in liquid helium at the corrosion temperature, the magnetic field always exists because the current you have passed once keeps on producing, because it keeps on moving. Current will be always there, not producing, currents will be always present. It is called a superconducting state. That means there is no opposition for the flow of electrons. The current, once you pass and generate the magnetic field, it persists forever, so long as you maintain the superconducting temperature. Now, as I have been discussing, what should be the homogeneity requirement? I said strong and homogeneous magnetic field. What is the homogeneity requirement? In a 500 megahertz spectrometer of 11.75 Tesla, I should be able to separate two frequencies separated by 0.1 hertz. If I know what is gamma of the proton, if I know what is the resolution I require, we can calculate. I did that earlier also once, I think. And this is about 2 in 10 to the power of minus 10. So our resolution should be of the order of 1 part in 10 to the power of 10. In a 1000 megahertz spectrometer, you must be able to separate 0.1 hertz. Imagine the homogeneity. That is the amount of resolution we require. So there is a heavy demand on the homogeneity of the magnetic field. Okay. So for the requirement of a superconducting magnet, first thing is high stability, its minimal drifts, and of course, this I already discussed. And if I look at the external view of a superconducting magnet, this is how it comes. Okay, this is how you see. But inside, if you see from the top, let us say, we have, this is the room temperature bore. This is where the probe is put. You put your sample. All your experiments are carried out at room temperature. Surrounding that, we have a liquid helium chamber. RF coil is superconducting coil, not RF. Superconducting coil is inserted, dipped into the liquid helium here, which is at 4K. And surrounding that, we have a liquid nitrogen chamber. This is to minimize the evaporation of liquid helium. And in between, we have lots of things, vacuum, and also mylar films, etc., to minimize the evaporation of helium and nitrogen so that it can last for a longer duration. And look at this. If I peep inside more and more, this is the liquid helium filling port. You will see in the magnet. Go to the NMR lab, you see a huge cylindrical like material will be standing there. That is a superconducting magnet. You have several ports like this. This is for liquid helium filling. This is for liquid nitrogen filling. We have a RF coil here. This is a sample holder. And then sample is put inside this. This is a probe. Okay. This is the coil. Superconducting coil is here. It is dipped in liquid helium chamber. And this is the liquid nitrogen chamber. So very simple. Basically, it is a highest quality, most sophisticated quality of a thermos flask. That's all. I mean, I cannot make it so cheap statement. It is not that. This is a superconducting magnet. Technology is highly different. Okay. So, but the concept you can imagine like a thermos flask. Now, cross-sectional view of a superconducting magnet. If you look at it, if you take a constrictional view, you see this is the inner bore where it is room temperature. Probe is put. All your samples are here. You can the probe. You do the experiment at room temperature. You saw concentric circles like this. helium filling chamber, we have a casing, a outer vacuum, shim coils, main this superconducting windings are there, while, and then we have a shield inside. Between the liquid nitrogen, liquid helium chamber, there is enormous shielding to prevent the evaporation, and you have to make sure that helium do not evaporate faster, nitrogen do not evaporate faster. There must be, everything must be in a high vacuum. All those things are taken care. And to get a homogeneous magnetic field of such a very high magnetic field is a challenging task. Remember, that's the reason why almost 50% of the cost of the spectrometer goes for the magnet itself. Because a lot of research work is, a lot of technological development is going on to get a very sophisticated magnet of our requirement. It involves a lot of efforts. So as a consequence, when you buy a spectrometer, major portion of your money goes to the magnet part. So now, as I said, even though magnet is superconducting, the bore is at the room temperature. All samples are investigated only at room temperature. Okay. Now next, what are the advantages of a superconducting magnet? First thing, you can achieve highest field, which is not possible to achieve in a iron core magnets, permanent or electromagnet. There is a limitation of 2.5 Tesla. Here, maximum possible line, now it is 24 to 27 Tesla, we can easily achieve. Magnetic field is stable and homogeneous. And the running cost is low. Of course, we have to take into account the liquid helium and liquid nitrogen, which we have to constantly keep on replenishing when it evaporates. That itself is a lot of cost for the maintenance. This statement we have to take with a little pinch of salt. This is said because we don't need electric power regularly, etc. Once you pass the current, you are in a superconducting state and the magnet is always maintained. That is the reason. But of course, helium requirement is there. Nitrogen requirement is there. Liquid helium and liquid nitrogen, very expensive. Constant requirement. We have to constantly replenishing, keep filling it when it evaporates. So that is a very, very huge running cost. And of course, basically, if you have high field spectrometers, NMR spectrometer has a lot of advantages. We have high chemical shift dispersion, improved selectivity in the spectral editing scheme. Sensitivity goes up by B0 to the power of 3 by 2. Remember, higher the magnetic field, higher the sensitivity. Spectral simplification is possible. We can get first order analysis. Like I said, second order spins which are coupled. Second order coupling, if it is a high, strongly coupled spins, can become weakly coupled, and first order analysis is feasible at very high magnetic field. We can see Trosi effects, which I did not discuss, don't worry about it. T1 increase at high field, a small disadvantage, doesn't matter. We can study T1 also. So now to get a homogeneous magnetic field, in general, all the magnetic fields, when you make a magnetic field, it is not that it is perfectly homogeneous. Over a sample volume of 3 or 4 centimeters at the rate of 1 part in 10 to the power 10 homogeneity. It is not always true. Cannot happen. We need to, there will be inherent inhomogeneities. We need to correct it. The static field has to be highly homogeneous across the sample. Otherwise, you will get distorted line shapes, broadened peaks. For what you will do for that? We have what are called shim systems. Inside the magnet, we have in the probe, just inside the magnet at the outer chamber, you have what are called shim system. It's a device used to correct locally varying fields. Locally, there will be inhomogeneities in the field, and we can correct that. And for that, what is the shim unit? It is nothing but contains a small coils of wire which is supplied with regulated currents. I can regulate the current flow inside the coil, and they are all in a different shape. It's kept in different shapes at different places, positions, such that if there is inhomogeneity along z-axis or x-axis or y-axis, I can put a counteracting current and generate a counteracting magnetic field to nullify the inhomogeneity. I can cancel out inhomogeneities created by the main superconducting coil. So these are the advantages. We have a shim unit, we can correct the magnetic field. But this shim correct magnetic field inhomogeneity can be both at cryo shims and room temperature shim. When you have inserted in the superconducting material in the liquid helium chamber, when you are passing the current, At that time, also we have to homogenize. That is called cryoshims. And afterwards, we have to homogenize this at the room temperature when you are routinely doing the samples. This you do not touch regularly. Once it is done, at the time of the charging the magnet, nobody is going to touch it. You are not allowed to touch, you can't do it. Whereas these things, room temperature shims are in our hands. As I always say, you have to get good homogeneity. You have to utilize these room temperature shim coils. There are about 24 to 36 different shim coils will be there, like Z, Z1, Z2, Z3 up to Z6 gradients, X, Y in different directions. You can the counteracting magnetic field can be produced to cancel out the inhomogeneity. There are several like this. And magnetic fields produced by the shim currents can be given by a mathematical expression like this. You can expand like a Taylor series. B is going to B naught main field plus additional field X variation, and the deviation on the X axis, Y axis, Z axis, X squared, XY, all these components of the Taylor expression you can consider. And each shim coil will produce a tiny magnetic field with a particular spatial profile and acts as a gradient to cancel out the residual inhomogeneities that is produced by the main field. So this is not, that's why you can have expansion of this for n number of terms. That is why we have different shim coils. So you can vary the magnetic field in X direction, Y direction, Z direction, X squared, that is a parabolic path, X, Y, X cube in a different shim. These are all shim coils where you can change produce the counteracting magnetic field in different spatial profile. So shapes of the shim gradients, you can consider a first order gradient produces a linear variation like a Z, X, Y. Second order is quadratic like X squared, Y squared, etc. Third order is cubic variations. Okay, Z order, Z gradient is of course independent of X and Y, increases linearly with the Z. And it can be treated like a PZ atomic orbital. Okay, and XY gradient is independent of Z and has a shape of like a DXY atomic orbital. So this is all you can have a similarity with atomic orbitals. Inhomogeneity of the magnetic field, how the shim current spatial profiles are produced by the different magnetic fields are produced with a different spatial profile with the different shim coils. So you can keep on changing it. You can have three independent shim coils combined together. You can produce magnetic field gradient in any direction you want. You all know. Since it is a chemistry course, you know that if I have three orthogonal p atomic orbital, it can constitute a closed shell. This is an analogy. If I have three independent first order gradients, I can combine them in various fashions and produce a first order gradient which can point in any arbitrary direction of my choice. That's how all 36 shim gradients have been designed. Okay. Similarly, five independent second order gradients can combine, give a second order gradient arbitrary. Third order can give like a F-like orbital shape. Like this, you can have many things to talk about it. So this is how you get a magnet, you can tune the magnet and everything. This magnet has to be maintained in a persistent current mode. That means you need to keep on filling liquid helium and liquid nitrogen. If liquid helium evaporates, magnet will suddenly achieve room temperature. Or at any instant of time, a small resistance is generated in the superconducting coil or a superconducting material by some reason. It generates heat. Remember what will happen to liquid helium? Liquid helium is at 4.2 K, 4.2 degree Kelvin. If you are familiar, if you want to make you more familiar, room temperature is 300 K. Remember, that is at 4.2 K. It is minus 269 degrees or 269 K lower than the room temperature. Such a low temperature. Small amount of heat when it is generated in the superconducting material, entire helium gets evaporated. That is called quench. It can happen for various reasons. Okay, magnet can start straight away without you doing anything. We have seen magnet quenching while filling liquid helium type, while charging. Many times we have seen magnet quench. And see magnet quench because of the increase in the temperature. Then when it happens, suddenly superconducting material enters into a non-conducting state. From superconducting state, it loses all superconducting state and attains resistance, gains a resistance which was zero before, and whole magnetic field is lost. Okay, so the helium boils off very rapidly, and the way you can see, if you really see the magnet quench, it looks like very dramatic. See here. You can see this is the quench which happened in our lab, in 1 or 2 years back while charging the magnet. You see, entire helium is boiling off and is very dangerous. Remember, when 1 liter of helium evaporates, it will evaporate into 27 liters of helium gas. It occupies the entire space. It can deplete oxygen. You see the point? Entire helium is getting evaporated now. It is coming out of the nozzle like this. We have to be extremely careful. This is called a quench. Okay. Now, with this, we'll go further. When the safety consideration, when magnet quenches, when helium gets evaporated, as I said, oxygen may get depleted in the room. It may cause asphyxiation. Can lead to fatal death also. Always open the doors and windows of the room while filling liquid helium and liquid nitrogen. Okay? Do not try to do the experiment by closing the doors and windows, filling the helium. If by some reason, if you are bad luck, if there's a quench, it can be very dangerous. So this is one of the safety warning I'm giving you. And sometimes magnet is so high, our homogeneity has to be so precise. We require such a good homogeneity. You may not know you have housed the magnet and you have charged and completely the magnet is kept on the floor. Some vehicle, heavy truck will be moving, let us say, in a main road far away, some 30 or 40 feet away or 50 feet away. The vibrations that is felt on the floor because of the movement of the vehicle can be seen by the spectrometer. The magnet starts fluctuating. These are all vibrations due to external disturbance. Floor vibrations can cause problems. As a consequence, you see, NMR spectrum gets distorted. So you have to ensure the magnet is put in a place which is free from floor vibrations. You will not see sometimes, the difference. You can check in case if it is not put on a vibration-free stand, anti-vibration stand, if it is put on a floor, if somebody is doing a work on a lathe or somewhere in a little far away, or a heavy truck is moving just 50, 20, 30, 40 feet away, your spectrum, you'll see a lot of disturbance will be there. You will start interpreting as due to sync function artifacts, etc. But this is due to external disturbance coming. Okay. So you have to mount it on this thing, on a anti-vibration stand. Now the question you may ask me, okay, I will tune the homogeneity, everything. But why should homogeneity get disturbed? When I charge the magnet, tune once and keep quiet. I shim the magnet, make the field homogeneous and keep quiet. Why should it get disturbed again? Why should I do it again and again? That's the question you may ask. Remember, the magnetic field homogeneity, microscopically, even if you get disturbed, it will be reflected in the spectrum. See, changing of the sample containing a different solvent. I have a solvent with sample prepared in chloroform. I tune it because it has a one diamagnetic susceptibility for that sample. I change that sample, put a different sample with a different solvent. Again, you will see susceptibility of the sample will be different, and because of that, field will be different. Homogeneity will be different. If you have a sample tube with different heights, if you don't take perfect height of the sample in the tube, you may get into problem. And you have to have the perfect height of the sample also inside the spinner, which should completely fit into the receiver coil. I'm sorry, RF coil in the probe. Otherwise, you may get distortions. And NMR tube from different manufacturers can be bad sometimes. You check yourself. Purchase NMR tubes from different manufacturers and do the experiment. There could be slight inhomogeneities. It may be different from different manufacturers. And if you can change the sample temperature, if you don't regulate, there is inhomogeneity, is a gradient in the temperature across the sample volume that can give rise to inhomogeneity. Many factors contribute like this. As a consequence, you take out the sample once, put the sample again, the same sample, you may have to retune the field to some extent. If you change a different sample, of course, no choice, you have to retune to get the better field homogeneity. So all these effects can give rise to a noticeable change in the line width and line shape. You have to take proper care, and every time you put a sample, when you change a sample, you have to tune the homogeneity. That's the important point. Okay. And how much it will change if I change the organic solvent? The diamagnetic susceptibility of organic solvent is of the order of 10 to the power of -7. So what happens when you remove an insect? It changes by nearly 100 parts in 10 to the power of 9. The gradients in the NMR probe will change of the order of 100 parts. So as a consequence, the field inhomogeneity will be developed. We need to tune it. Okay, what I'm going to do is next I will discuss something about the probe, which is another important component of the spectrometer, and then little bit about few other things. And I don't want to go into the more details of other components. Probe is an important part. I will discuss this in the next class. So I'm going to stop it now. We'll come back and continue with the instrument for some more time.